In today's video, we are going to take a look at volume of three-dimensional solids using something called the disk method. All right, it covers two topics, but they're basically the same thing. One is around axes and the other is not around axes. Okay, so let's start with remembering something from geometry. In geometry, you learned how to find the volume of a cylinder. The volume of a cylinder formula from your geometry days, hopefully you recall that, is volume equals pi r squared h. That's the formula we're going to use in every problem using this method. Of course, we're going to, instead of simply knowing what r is, it's going to be some type of function, and we're going to have to integrate it as it goes from the bottom bound to the upper bound. This disk method, using areas of the known cross-sections from the previous two topics, is not the only way calculus and a definite integral can be used to find volumes of 3D solids. The solids in this topic and next will focus on those with cross-sections that are all circular. A disk is basically a very short cylinder where the height h is actually the w value. The radius retains its actual meaning. The pi pops out in front, and you get the following formula below. So here we have a function called f of x. I'm going to rotate it around the axis, so around the x-axis. So what this is going to look like here, if you let's take a random point, this point right here. And I know it's hard to see 2 dimensions and 3 dimensions here, but you want to rotate, it's going to spin around the axis like that. And it's going to create a circle. And all of those points are going to do that. And what it's going to end up creating here is kind of like a 3-dimensional vase. All right, so the volume of a solid, a disk method solid formula, is going to be the integral from a to b of f of x minus a of x dx, where f of x is simply the function that you are rotating, revolving, and a of x is the axis of revolution. Of course, that is if we're revolving around some type of horizontal axis using the dx method. If we're talking about a vertical axis of revolution, we would be using dy method, which I already see a little typo here. This is supposed to be r of y squared dy. I'll fix that for your notes there. So how do I know? When you draw a little rectangle in, if we're going to move that rectangle left and right to fill the whole shape up, that's a horizontal axis of revolution. That's a dx problem. If we're going to move that rectangle up and down, okay, that's a dy problem. So a couple of generalizations before we take a look at our first problem here. Draw the function or functions that we're going to revolve. Determine the regions to rotate. And then if it's, like we talked about, rotate around a horizontal line, it's dx, and everything must be in terms of x. If it's about a vertical line, it's dy, and everything must be in terms of y. So let's take a look at our first problem here. And we're going to do some of these involving our calculator today. So go ahead and get your calculator ready as well. We'll try to do a couple by hand, but there might be some later on that we'll take a look using our calculator. Find the volume of the solid formula revolving the region bounded by the graphs of f of x equals sine x, so root sine x, and the x-axis about the x-axis. So root sine x and the x-axis. That's the region right there. It's going to spin around the x-axis. All right, let's draw it in our representative rectangle. There it is. To fill that region, we're going to move the rectangle left and right, which means this is a dx problem. Okay? So, remember our volume formula we talked about was pi r squared h, right? So our volume here is going to be pi. R is just function minus axis. So function be root sine x minus axis. The axis is y equals 0. And then h is dx or dy. In this case, it'd be dx. And our bounds, well, if you don't know your bounds, you can always set root sine x equal to 0, square both sides, and sine x equals 0 at 0 and pi. I forgot the square there. So here's our formula, pi r squared h. Okay, so pi r squared h. It's just a cylinder, but it's many cylinders. Okay, it's many. This is our one cylinder that we drew. All right, when we revolve this around, it's going to be a cylinder, a disk. But there's infinitely many, and that's what the integral does. It adds all those together. All right, so simplifying this before we take the antiderivative. It's no longer squared. The square and the square root cancel each other out. And now we can take our antiderivative. The antiderivative of sine is negative cosine, so negative, let me write this a little differently here. Negative pi times cosine of x from 0 to pi. So it's negative pi times cosine of pi, which is negative 1, minus cosine of 0, which is 1. So we have negative pi times negative 2, or 2 pi. So if we revolve that shaded region there around the x-axis, its volume would be 2 pi. Example 1b, find the volume of the solid formed by revolving the region bounded by the graph of f of x equals 0 on the x-axis about the x-axis. So this is our region here. Drawing our representative rectangle. Moving that left and right to fill the region, so it's a dx problem. So we're going to go volume equals pi. The bounds here are pretty easy to see, are 0 to 1. R, which is function minus axis squared, dx. So again, pi r squared h. Simplifying that, we get 1 minus x squared dx. All right, and for this one, let's use our calculator. Just to remind us how to use our calculator properly. So go to math number 9, 0 to 1, 1 minus x quantity squared dx. And we should get 1/3. So our answer is pi over 3. Question 2, now we're going to revolve this around a line that's not the axis. So we're taking f of x and above g is equal to 1. So this area right there, our representative rectangle, is we're going to revolve it around the line y equals 1, moving left and right. So it's going to be a dx problem again. So volume equals pi. Our bounds here, pretty easy to see again, are negative 1 and 1. If you don't see it, you can always set them equal to each other and solve. The radius here is function minus axis squared dx. So once again, pi r squared h. So pi, let's simplify this here. We have 1 minus x squared squared dx. Let's do this one by hand. So pi, we have to simplify this out to be 1 minus 2x squared minus x to the 4th, plus x to the 4th, dx. Taking our antiderivative would be x minus 2/3 x to the 3rd plus 1/5 x to the 5th from negative 1 to 1. So it's pi 1 minus 2/3 plus 1/5 minus negative 1 plus 2/3 minus 1/5. So that's pi. 1 plus 1 is 2. Negative 2/3, negative 2/3 is minus 4/3. 1/5 plus 1/5 is 2/5. All right, the common denominator there would be 15. So 30 over 15 minus 20 over 15 plus 6 over 15 would be 16 pi over 15. All right, example 3, integrating with respect to y in this one here. So find the volume solid of the solid formed by revolving the region bounded by the graph of f and the x-axis about the line x equals 3. So x equals 3 would be right about there. So there's our axis of revolution. This is our region that we're trying to revolve around it. Let's draw our representative rectangle towards the axis here. Okay, we're going to move that thing up and down to create this whole region. So it's going to be a dy problem, which means I need to solve this to be in terms of y. So it's going to be y squared equals x plus 1, and then y squared minus 1 equals x. All right, so our volume here is going to be pi times the integral. Remember, these are y bounds here, so the lowest y is 0. The highest y is 2. If you don't see that, you can always set these equal to each other to solve. So bounds are 0 and 2. R squared, so the radius here is going to be function minus axis squared dy. Pi r squared h. All right, let's do a little simplifying here. So pi, the integral from 0 to 2 of y squared minus 4 squared dy. And then let's use our calculator now to solve this one. So integrate from 0 to 2 of y squared minus 4 quantity squared dy. Now remember, in your calculator, you're using all x's. And we should get 256 over 15. So our answer is 256 pi over 15. Which brings us to our last problem. The two integral case. Why is it two integral case? Well, let's take a look and see. We're going to revolve the region bounded by x squared plus 1. So x squared plus 1 is going to look like that. Y equals 0. X equals 0. And x equals 1. So this is our region. About the y-axis. So if you did something down here, that would be a disk problem. However, if we did this over here, that's going to be something that is not a disk. Okay? So, right now, we are not able to do this problem. Okay, I want to just get you thinking about how we would do this. Right now, we could only do this part, but we cannot figure out this part because there's a hole between our region and the axis that we're trying to spin this around in. So, in our next lesson, we're going to talk about something called a washer. Okay? And then that washer will allow us to do this region. And then once we can do that, we can add this one to this one and get our total volume. All right? But for now, let's just keep it where it's at. We have our picture. We know what we're going to need to do, and we'll learn how to do this in our next video. All right, and that will do it for our notes on topic 8.9 and 8.10. Thanks, as always, for looking into this video today.